Hey everyone, and welcome to The Explainer. Today, we are unpacking a really fascinating story. We're going to look at a revolutionary scientific hypothesis, its tragic ultimate flaws, and how science actually progresses. Because, science doesn't just move forward by getting things right, it also moves forward by getting things spectacularly wrong. We are going to be looking at J.J. Thomson's Plum Pudding Model of the atom. And I promise you, by the end of this, you'll see exactly why even failed ideas can be absolute brilliant triumphs.
So I want you to start by just asking yourself, what does the universe look like on the inside? I mean, really imagine you're a scientist back in the 1800s. You know matter exists, right? You know things have mass. But when it comes down to the fundamental building blocks of reality, the atom itself, it is just a total impenetrable mystery. You can't see it, you can't touch it, and you certainly don't have a clue what it's actually made of.
Part 1. The untouchable atom.
So for a really long time, early scientists like John Dalton, they believed atoms were simply indivisible. They thought of them basically like solid, indestructible billiard balls, nothing inside. But of course, that didn't last forever. The 1800s were totally dominated by Dalton's idea. But then, boom, 1897 happens. J.J. Thomson is in his lab conducting these cathode ray experiments, and he discovers something that should have been absolutely impossible according to Dalton. He discovers the electron, a tiny, negatively charged particle that came directly from inside the atom. This literally changed everything. It proved the atom actually has an internal structure. It wasn't the end of the line after all. And so, to explain this massive, game-changing shift, Thomson proposed a brand new theory in 1904. The Plum Pudding Model.
Okay, let's dive into this, a revolutionary recipe.
So, Thomson had this puzzle. He had to figure out a way to fit this newly discovered, tiny, negative electron into a stable atom. And to help people visualize what is honestly a highly abstract physics concept, he used a very tangible, everyday object, a plum pudding. Now, for those of us who aren't super familiar with 19th century British desserts, you can just think of a blueberry muffin or maybe a chocolate chip cookie. He proposed that the atom is basically a uniform pudding of positive charge, and those newly discovered negatively charged electrons, they're the plums, just scattered and embedded right inside of it. The pudding is the positive, the plums are the negative. It's a wonderfully simple analogy that instantly helped the whole world visualize the invisible internal structure of an atom.
Moving on to Part 3, Inside the Pudding.
Okay, if you're taking notes and you ever need an exam-ready definition, here it is. Thomson's Plum Pudding Model states that an atom is a sphere of uniformly distributed positive charge in which electrons are embedded such that the atom as a whole remains electrically neutral. Now, every single word in that definition is deliberate. You've got a sphere, the positive charge is spread out completely evenly, so uniformly, and the electrons are stuck inside to perfectly balance the whole thing out.
And actually, here's a fantastic little trick to cement this in your mind forever. If you ever blank on a test, just remember the PPP rule. First P, positive sphere. Second P, plums, which represent the electrons. And the third P, pudding analogy. If you can just remember PPP, you can completely reconstruct Thomson's entire theory from scratch right there in your head. Positive sphere, plum electrons, pudding analogy. Simple as that.
Now, the absolutely crucial point to remember here is that the net charge equals 0. This is the foundational bedrock of the whole model. See, we already knew from everyday observation that atoms are electrically neutral. I mean, they don't just go around shocking us, right? So Thomson applied some really solid logical reasoning. Since he just discovered electrons are negative, there absolutely must be an equal amount of positive charge somewhere in there to balance them out. So the total positive charge of the pudding perfectly cancels out the total negative charge of the plum electrons.
Let's walk step by step through the rest of the features of Thomson's atom. Number 1, like we mentioned, that positive charge isn't concentrated in one spot, it's uniformly spread everywhere. Number 2, the electrons aren't actually totally frozen in place. They're somewhat mobile, kind of just held there by the electrostatic attraction to all that positive pudding around them. Number 3, and I really want to emphasize this one, there is absolutely no empty space. In this model, Thomson's atom is completely densely stuffed full. And finally, number 4, this arrangement of electrons actually began to partially explain chemical valency and bonding, which was a huge step forward for the field of chemistry.
Which brings us to the next section, the fatal flaws.
Now, what's really interesting about this slide is how methodically this beautiful, elegant model just broke down under the harsh scrutiny of new experiments. The biggest, most dramatic blow was the famous gold foil experiment by Ernest Rutherford. When Rutherford shot alpha particles at gold atoms, some of them bounced wildly off course, showing these massive, completely unexpected deflections. Think about it. If atoms were just soft, uniform puddings, those high-speed particles should have just shot straight through, like a bullet through tissue paper. The model also failed to explain why electrons didn't just collapse directly into that positive charge. It completely failed to explain the specific line spectra of elements. And most importantly, it had absolutely no concept of a nucleus to explain where all the actual mass of the atom was hiding.
Section 5. A new nuclear reality.
Let's move to and see how this builds, because those fatal flaws meant the scientific evidence basically demanded a totally new explanation. It permanently dethroned Thomson's idea, and this created a completely different picture of reality for us. Look at side A versus side B here. Instead of Thomson's solid sphere of spread-out positive charge with embedded electrons and literally zero empty space, Rutherford introduced our modern understanding. It turns out the atom is almost entirely empty space. The positive charge isn't spread out at all. It is highly, highly concentrated in a tiny, dense central core that we call the nucleus. And the electrons? They aren't embedded like plums. They're actively orbiting that nucleus. It is a stunning, massive contrast from where we started.
And finally, the enduring legacy.
So Thomson was wrong. His model was totally replaced in just a few short years. But does that make it a failure? Absolutely not. So why did the plum pudding actually matter? Because it was the very first model to ever show the internal structure of an atom. It shattered Dalton's indestructible billiard ball myth and introduced the entire world to subatomic particles. It acted as this vital, completely necessary bridge between classical physics and the modern atomic theories that would eventually give us quantum mechanics. And honestly, most poetically of all, it directly inspired Ernest Rutherford's experiments. Rutherford was actually trying to prove his former teacher's model right when he accidentally proved it wrong. And guys, that is the scientific method at its absolute finest. Theories are meant to be broken so we can build better ones.
And that brings us to our final thought. The plum pudding model was the absolute cutting-edge fact of its day, until it wasn't. So I want to leave you with this. If the facts of today can be the plum puddings of tomorrow, what current, widely accepted scientific theory is just waiting to be rewritten right now? What are we totally wrong about today? Keep questioning, keep learning, and thank you so much for joining me on this explainer. See you next time.